Hello everyone, we will talk about the DC machines. So as we know from the motor and generator operation, if we convert DC electrical energy to the mechanical energy, we have DC motor operation, or if we will convert mechanical energy to a DC electrical, in that case we have the DC generator operation. In terms of the DC machines, we can say they have wide range, speed and power. So because of this, in different applications, we can see the DC machines as motor or generator. And there, when we compare with the similar power ratings of the other types of the machines, they are efficient and they have superior torque characteristics. Because of this, especially in the railway and EV vehicles, we can see the DC motors to control the systems. But they are expensive when we compare, especially with the induction machines. The reason of this one, their construction, and in the industrial case, they have bars to transfer the voltage from terminal to the rotor part, or from rotor to the terminal part. They have commutator structure and the bars, so they need extra regular maintenance and extra cost because of this. As we discussed in the induction motor, we have two parts, rotor and stator, and between them we have an air gap to transfer the magnetic field. Similar construction we have in the DC machines, but we have additional names for the rotor part and the stator part, especially if we are talking about an excitation inside the machine to induce a voltage. The windings are called as armature and the field sides. So in the rotor, we will call it as armature, and the windings located on the rotor part are called as armature windings. And similarly, the field windings are located on the stationary part, which is called as field in such constructions. Okay, what about the induced voltage, produced voltage inside the machine? How can we obtain this one? So EA, which is the induced voltage as a result of the applied voltage to the terminals, it can be defined as Z, which represents the total number of conductors, radius of the machine, Wm, which represents the motor angular velocity in radian per second, and in that machine there is no synchronous speed. The speed of the machine will be the motor speed. And the magnetic field density, length of the motor divided by A, and A represents the number of current paths which are designed inside the machine. So we can modify this expression, the induced voltage, to be able to create an analogy between the flux and the induced voltage. So when you divide and multiply with 2 pi p, p again will represent the pole number of the machine. EA can be rewritten as, first of all, let's combine some of the constants. Then the remaining part will be, first of all, 2 pi RL over P, which is the per pole cross-sectional area. Then the magnetic field, magnetic field density, and the Wm. So when we examine this expression, the first part, which includes only the constant terms, so because of this, it can be grouped and it will be the machine constant K. Why? Because Z is a constant. After the construction, we cannot change these values. Z, which is the number of conductors, P, pole number, 2 pi is a constant, and A, total number of current paths. For the second part, 2 pi RL B over P, which shows the flux of the motor. So again, it will be the second parameter of the induced voltage equation and the velocity. So we can write this equation as K machine constant, flux, and Wm, which is the velocity. So this is an important expression. Why? Because during the motor operation or generator operation, when we want to analyze the characteristics, we have two parameters in this expression. We can change the velocity and we can observe the flux and EA variation, or we can try the same situation by changing the flux and how much speed will be affected, or EA speed relation can be obtained. So to obtain the characteristics of the DC machine, this equation has an important meaning. Similar with this one, by the way, the W, radian per second rotational speed, also can be modified as RPM speed, and the coefficients can be integrated with K. We have a similar expression. If we skip the details, briefly, we can write the induced torque expression as K, phi, and the armature current. This is also explains the relation between phi, the flux, and the induced torque, or armature current and the induced torque. So we can analyze the relation between them by keeping constant one of the right side parameter. Flux or armature current can be keep as a constant, and we can check the other two relations. So these expressions will be important for the excited machines. That means for the DC machines, and the following system will be synchronous machines. Also, these expressions will be important to understand the relations of the parameters and to obtain the characteristics of the machine. So, for the DC motor and the generator operation, if we want to analyze, regulation will be important. For DC motor or DC generator, our parameters, the output parameters for generator will be speed. How much our rotational speed we have, what is the output motor speed will be according to our operating conditions, we need to clarify. So because of this, similar with the most of the system actually, from the no load to full load variation, how much speed difference as a ratio, what's the relative difference, we need to clarify to understand the performance of the DC motor. So the speed regulation can be obtained with the no load speed and full load speed difference divided by full load speed. As a percentage, we can calculate this value. So theoretically, there is no problem with this expression. In the numerator part, we have a difference between no load and the full load speeds. But in the practical case, no load operation has some unexpected situations. Because of this, instead of no load speed, or the first parameter, instead of no load parameter to calculate the regulation, we prefer to use 10%, around 10% load case, because at 10% the system will be more stable operation. So in that case, we can find a more correct result for the regulation parameter. And for the DC generator, similar case we have, and to determine the value of output voltage, because for this case we will see what will be the output voltage of the output voltage change of the DC generator. It will be important for us. So because of this, for the DC generator, we can write the voltage regulation parameter. And it will be, we will start with the no load value, then we will subtract the full load output value of the system to understand the regulation. So the terminal no load voltage minus terminal full load voltage divided by terminal full load value as a percentage can be calculated. Okay, so let's talk about the excitation types. In the DC machines, excitation types are classified according to armature and the field side connections. So because of this, let's start with the equivalent circuit of the DC machine. So for the equivalent circuit, we have two parts, rotor and the stator in the electrical part. So let's start with the stator. In the stator, we have field resistance and field inductance. So the first one will be the adjustable resistance, and which represents the field, a part of field resistance. It can be adjustable to adjust to be able to change the flux value, because between the flux and the field current we have a relation. So by changing the resistance, we can control the current which is flowing through that part, and we can control the flux amount. And it will be important for this expression, because if we can control the flux, that means we can control the EA, induced internal voltage. So the second parameter is RF, but we can lump these two resistances together and we can show with a single field resistance. But we should remember if we need to adjust the field current, these resistances can be changed by adding extra external resistances, or with other ways we can adjust them to control the IF. Other parameter will be the inductance of the field circuit, and for that part the voltage applied to the field circuit will be VF and the field current IF. So this part is located on the stator, and which is called as field winding. So after we apply the VF, or the field winding voltage, to the circuit, there will be a current. And according to our induced internal generated voltage expression, it will produce the EA. And this internal generated voltage parameter can be shown on rotor part for the armature winding, armature circuit. Then for that part, we can integrate the brush effect. It will be the changing voltage. So brush voltage drop can be shown on the armature circuit also. And in addition to that, we have an armature resistance. And this part will be the terminal voltage. So for the motor operation, we will supply from the terminal side Or if we have a generator operation, we will take the voltage to output from this terminal points. So because of this, if we have a motor operation, the line current must show the inside for the motor operation. And if we have a generator operation, IL will be out. For the armature circuit, also the voltage, after we apply the voltage or in the generator operation, the current direction must change. For the motor and for the generator, armature current direction will be reversed. Okay, this is the general equivalent circuit of DC machine. In motor or generator operation, only IA and IL directions will change. IF direction will remain same. EA polarity will remain same. In addition to that, after we apply the voltage or during our voltage output, our mechanical part can be shown through the EA. So the shaft in the equivalent circuit should be connected to EA, and according to our operation, WM can be taken or can be applied from this point. This is the general equivalent circuit. So when we examine the magnetization curve of the system, we need to examine this expression, internal generated voltage. If we have a constant speed, EA, if we combine all the constants together, EA will be the function of flux from here. So we can say EA will be the function of flux during the constant speed, and the flux is the function of B, magnetic field density, because B times A, cross-sectional area, gives us the flux, and we cannot change the cross-sectional area also. Then the B will be the function of magnetic field intensity, which is representing the Ampere's law. So the number of turns, L, the length of the mean path length cannot change. So because of this, H will remain constant. The relation between B and H will remain constant. And after that, the current to produce this magnetic field will be IF. So initially the cross-sectional area will be active as a constant, then the permeability between B and H, and after H, the current H relation will be the function of the equation to control the EA. So briefly, we can say EA will be the function of IF when we combine all the constants. And when we examine its characteristics, we have a classical magnetization curve. With respect to IF, the EA variation will start with the linear part. Then after the knee, we have a constant values, nearly constant values for EA. Until to knee, if we increase the IF step by step, we have the linear variation, the increment parts values will be same. But after knee, we can increase IF with the same increments, but EA will remain nearly constant. Until to where we will increase IF, until to rated value of the machine, we should obtain the magnetization curve of the DC machine. Okay, now we can talk about the excitation types. We have 4 different excitations. These are separately excited, DC machine, shunt excited DC machine, series excited DC machine, and finally compound excited DC machine. So for each of them, we are checking the connection between the armature and the field side. What is the connection type between them? We will analyze. We will continue with the excitation types of the DC machine as motor and generator operation with their equivalent circuits and the steady state expressions. Thank you for watching.